Okay, so in this module, we're going to discuss some of the aspects associated with nuclear chemistry. And one of the things in terms of nuclear chemistry is that it's very applicable to things that go on in the medical field. Essentially your MRIs, your CT scans, being injected even, with radioisotopes as part of these processes or even outside of that. It all involves some ideas that we're going to discuss in terms of nuclear chemistry. So, one of the things to highlight here is there really is a lot of practical applications in the medical and, science fields, especially the medical fields with nuclear chemistry. So we're going to start by taking a look at isotopes and radiation. So let's remember what isotopes are. Isotopes are atoms of the same element that have different numbers of neutrons associated with them. So essentially, their atomic numbers are the same, but their mass numbers are different. Most of the elements in the periodic table actually contain certain percentages of isotopes of that element. For example, hydrogen, there are three essential isotopes of hydrogen: hydrogen, deuterium, and tritium. Hydrogen with a mass number of 1 is commonly known as hydrogen. Hydrogen with a mass number of 2 is known as deuterium, and hydrogen with a mass number of 3 is what is known as tritium. The hydrogen atom has no neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. They are essentially isotopes of hydrogen. Now, it turns out that elements with atomic numbers of 20 and higher usually have one or more isotopes with unstable nuclei. And an unstable nucleus is radioactive, emitting small particles of energy called radiation to become more stable. So one of the things just to mention at this point is the usual relationship between energy and stability. Usually, the higher in energy you are, the less stable that you are. And then usually, the lower in energy that you are, the more stable that you are. And you think about, just think about yourself a little bit. If you're in a lower energy, if you have a nice, calm energy environment that you're experiencing, you're probably pretty relaxed. However, if you're in a very chaotic environment, very high energy environment, you're probably feeling very on edge. Less stable, higher energy environment, more stable, lower in energy environment. Common analogy sometimes that I like to use to try to explain the usual trend that we have between energy and stability. Now, radiation may take different forms. You could have alpha particles, where alpha a lot of times is abbreviated by the Greek symbol for A. Beta particles, which a lot of times are abbreviated by the Greek symbol for beta. Positrons, which we'll learn are essentially beta particles that have a positive charge, so they're not the same as beta particles. They just have an opposite. They're basically same content as a beta particle in a sense, but they have a positive charge associated with them. And then, well, I shouldn't say same content. Similar content-wise between beta particles and positrons. Essentially, their charge is just opposite. And then pure energy, such as gamma rays. Gamma, often abbreviated by the Greek symbol for gamma. Okay. So in a sense, what's one of the differences in terms of looking at pure energy versus the other three types: alpha particles, beta particles, and positrons? And positrons essentially would be particles as well. One of the things to consider is that, and we'll see this, is that when particles are released from actual particles, are released from an unstable nucleus, a change takes place in the number of protons in the nucleus of that atom. Whereas for when gamma rays are released, in these particular cases, no change in the number of protons takes place in the nucleus of that atom. Now, each one of these radiation, each time these radiation forms are released, an unstable nucleus becomes lower in energy and more stable. But for the first three, your alpha particles, beta particles, and positrons, an actual change takes place in the number of protons. So what's going to happen is that the identity of the element is going to change. Because remember, elements are identified by the number of protons they consist of. If you change the number of protons, you change the identity of the element. Now for gamma rays, when gamma rays are released, again, the higher energy unstable nucleus becomes a lower energy, more stable nucleus, but the identity of the element does not change. So to me, that's another way to distinguish between these, particles that are released versus something pure energy, such as a gamma ray. So that's a distinguishing feature I always like to bring up. And we'll see that as we go through our discussions. Okay. So an isotope of an element that emits radiation is called a radioisotope. Now, when radiation is emitted by a radioisotope, it may undergo a change in the number of protons, especially if it releases an alpha particle, or if it does release an alpha particle, a beta particle, or a positron, which means that it may be converted, and I'll put an arrow there, a sort of a breaker. It may be converted to an atom of another element. So one of the things that we'll talk about is that over time, for a radioisotope that emits alpha particles, beta particles, or positrons, the amount that you have of that is going to become less and less. Because if their identity is going to change, then there's going to be less and less of it when the identity changes. The idea that a lot of these radioisotopes change their identity is really totally different from a chemical reaction. Because when we talked about a chemical reaction, we talked about the fact that atoms cannot be created, destroyed, or changed into atoms of other elements. We saw that the chemical bonds between the reactants are broken and new bonds are formed to give the products. But the number of atoms of each element that you have doesn't change. Nuclear reactions, nuclear equations are a totally different ballgame, because in most instances, over time, as these different forms of radiation are released, the identity of the element is going to change. So nuclear equations, nuclear reactions are a lot different than chemical equations and chemical reactions. So one of the ways that we express radioisotopes are as their atomic symbols. So for an atomic symbol, we have the chemical symbol, and we talked about this previously in our discussions of isotopes in general before. We put the chemical symbol in the middle, and then in the upper left, we put the mass number, okay, of that isotope. And then in the bottom left, we put the atomic number of that isotope. So one example of a radioactive isotope is iodine-131. Even though you wouldn't know it just from looking at it, this is something you'd actually have to know from studying it, or something we would just have to tell you. Iodine-131 is a beta emitter. It spontaneously releases beta particles. So a lot of times, in terms of a shortcut, instead of writing the atomic symbol, and this is what we're talking about on the bottom here, instead of writing the atomic symbol, if we want to specifically mention about an isotope of an element, we can give the name of the element followed by the mass number. So in this case, we're talking about iodine with a mass number of 131. So I could write iodine-131. Or even shorter than that, instead of writing the name of the element, I could use the chemical symbol of the element, followed by the mass number, which again in this case is 131. So here are some examples. You don't have to memorize these or anything like that. What they're trying to show you here is, for example, with magnesium, which essentially you have a couple different isotopes. And I think there's even more than what's listed here. You have magnesium-24, which is stable, won't spontaneously release radiation. But then magnesium with a mass number of 23 and magnesium with a mass number of 27, those are unstable isotopes. So they're going to release radiation. Look at iodine. Iodine with a mass number of 127 is a stable isotope, doesn't spontaneously release radiation. But iodine with a mass number of 125 and iodine with a mass number of 131, both are radioactive isotopes. They will spontaneously release radiation. Now, for uranium, there are actually no stable isotopes. All the isotopes of uranium are radioactive, and including uranium-235 and uranium-238. I don't know if there's any others for uranium. Honestly, I don't know all the radioisotopes or elements off the top of my head. It's really not much important to memorize. Again, I'm not going to ask you specifics about this slide, but just to show you that for elements, where you have isotopes of that element, you could have some isotopes that are stable versus others which are radioactive. And in case of uranium, you actually have all the isotopes being radioactive.